My name is George Zikilic, and I will talk about the work on differential cost analysis with simultaneous potentials and anti-potentials. This is joint work with Borju Hevan-Cheng, Pauline Bolignano, and Franco Raimondi, and it was done mostly at Amazon. So before I start talking about our work, let me briefly motivate the problem that differential cost analysis considers. So suppose that you're a software developer and you write a new piece of code on top of the existing code base. Then, as a part of a standard software development pipeline, code goes to code review, where you might use your favorite static analyzer to detect hard bugs such as null pointer exceptions or some array index possibly being out of range. But in addition to being warned about hard bugs, it would be great if static analysis could also warn us about potential performance regressions. So for instance, if runtime has tripled compared to the previous code version, then developer with this information can check if this is something that they're fine with, or if perhaps this is an unintentional consequence that has performance implications. And the question that we ask here is, can we statically detect performance regressions the same way that we use static analysis to detect hard bugs? Differential cost analysis is a type of static analysis which considers exactly this problem, so it has also been considered in previous work, of course. And assuming that we have a well-defined notion of cost in programs, which is a quantitative property of a program execution, can be runtime, memory usage, number of object or thread allocations, so we can have both positive and negative costs. For instance, you can both allocate or deallocate memory. The goal of differential cost analysis is to prove a differential cost threshold assertion, so that the difference in cost usage between two programs does not exceed some threshold value t. Or even better, we might want to compute the threshold values for which the assertion is satisfied. So let me demonstrate on a simple example what we want to achieve. So suppose that we have two code versions. On the left and on the right, both programs take two integer arrays as inputs, a and b. We assume that both arrays have length between 1 and 100. And then in the old version on the left, we use cost variable to track the cost usage. So the program first iterates for array A. Then in every loop iteration, it iterates for array B. And in every inner loop iteration, it makes a call to a function f, which does something resulting in incurring cost 1. Now, on the right, we have a new code version which changes this as follows. So first, we swap the ordering between the loops. So we first iterate through B, and then we iterate through A. And then second change is that we modified the function f itself such that it incurs cost 2 on every call. Now, if you, by inspection, you can see that on input a, b, the difference in cost usage between these two programs is length a times length b. So because the maximal value that this can have is 100 times 100 equals 10,000, t equals 10,000 would be a threshold value for this example, whereas t equals 9,999 would not. And we want to develop an approach which would be able to verify that 10,000 is a threshold value, or even better, to compute 10,000 as the tightest possible one. Let me just note, while in this example threshold values are concrete values, we can also talk about verifying some symbolic expression thresholds. And in this work, we present a new approach to differential cost analysis, which is based on potential and anti-potential functions. So potential functions are a classical tool from amortized analysis, which has been extensively used in computing upper bounds on cost usage in programs. And anti-potential functions are their analog for lower bounds. So this is not the standard term. Like there are actually much fewer works which consider lower bounds, and they propose some variants of what we call anti-potential functions, but because there's not a single standard name, just for duality, here we call them anti-potential functions. And what our method does for differential cost analysis is you would first compute a potential function for the new program, so an upper bound on cost usage, anti-potential function for the old program, so their difference is an upper bound on the difference in cost usage between two programs. Now, if you do these computations individually, then these two computations would not be aware of the overall goal of reasoning about the difference in cost usage. Therefore, you might have imprecision. And to avoid this limitation, the key idea behind our approach is to perform this computation simultaneously. So we compute both functions at the same time in a way which is aware of the overall goal of reasoning about the difference in cost usage. So let me start by firstly formalizing what we mean by potential and anti-potential functions. So to formally define them, we model programs via transition systems. Potential infinitely many states moving from state to state. And then potential function is a function which maps states to real values, which satisfies the following two conditions. So first, when you have a transition from S to S prime, you want the value of your function to decrease at least by cost incurred by taking this transition. In other words, f provides enough potential to move from S to S prime. And then once you terminate, I forgot to mention, we assume that our programs are terminating, which is a necessary assumption for soundness. Once we terminate, the value of the function is non-negative. So I claim that function satisfying these two properties, when evaluated at some initial state, is an upper bound on cost usage incurred by a program execution. So to see this, let's take a terminating program execution. Let's start from the terminal state and traverse the execution backwards. So the terminal state, the value is non-negative. And then as you go backwards, traversing every transition, the value of f increases at least by cost incurred by the transition. Therefore, simple inductive argument on the length of the execution shows that f evaluates an upper bound on cost usage. Now, anti-potential functions are defined in a very similar way. You just follow the directions of inequalities. So f decreases at most by cost incurred by a transition and is non-positive upon termination. And the same inductive argument shows that it evaluates to a lower bound on cost usage. Okay, how do we use this for differential cost analysis? Well, if you want to prove that t is a threshold bound, then it suffices to find a potential function for the new program, so an upper bound, anti-potential function for the old program. Their difference is an upper bound on difference, such that for every initial state, this difference is less or equal than t. Then these two functions prove that t is a threshold bound. We can actually also use potential and anti-potential functions to refute or to disprove a threshold bound. So to do this, we do the opposite. Anti-potential function for the new, potential for the old. Now their difference is a lower bound on the difference in cost usage, such that at some initial state, their difference strictly exceeds t. Now these two functions witness that t is not the threshold value. Going back to our example, so here xi old for the old program and phi new for the new program exactly captures the cost usage in these two programs. So actually you can show that these are both potential and anti-potential function in each programs. So their difference at an initial state is length a times length b. So because we assume that arrays have lengths between 1 and 100, t equals 10,000 is witnessed by these two functions to be a threshold value when we treat them as potential and anti-potential. T equals 9,999 is witnessed not to be a threshold value. Okay. And so far, we have introduced potential and anti-potential functions, explained how they can be used for differential cost analysis. But of course, the key question is how do we effectively compute them? And remember, we don't want these computations to be separate. We want to do them simultaneously in a way which reasons about the difference in cost usage. So we achieve this by employing a template-based synthesis. So our approach consists of 4 steps, and it simultaneously computes these two functions together with the threshold. So as I said, in here we will also consider computation of the threshold. If we wanted to actually verify a given threshold value, then we will plug in, instead of the threshold that we compute, actually either concrete value or a symbolic expression or program variables that we want to verify. So our method assumes that provided programs are numerical programs with polynomial arithmetic, and it also searches for these functions as polynomial expressions. So template looks as follows. For the potential function, at each location in the new program, we will fix a symbolic polynomial expression over program variables of some given maximal polynomial degree, which is an algorithm parameter. And similarly, for anti-potential function in the old program, at every location we fix a symbolic polynomial expression. And then potential function, actually, to get its value at some state, at the corresponding location, you will evaluate the function, and that's it. And we also, as I said, we fix a symbolic variable for the threshold value t. Now that we have fixed our templates, we collect all the defining constraints that encode that PF and anti-PF indeed witness this threshold value. So PF and anti-PF, these are the conditions that I defined in one of the previous slides. And in addition, we have one relational constraint, which says that at every initial state, the difference in values between the potential and the anti-potential function is less or equal than t. So now we have a constraint which reasons about the difference in cost usage. Now, the resulting system of constraints contains universal quantifiers for every state, blah, 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 contains polynomial expressions. Of course, this is challenging for efficient synthesis. In order to overcome this challenge, we translate the resulting system of constraints into a purely existentially quantified system of linear constraints, i.e. a linear program without the optimization objective, by using a result called Handelman's theorem. Handelman's theorem is a result from algebraic geometry, which has also been used in some other program analysis, and we actually show that for our template-based synthesis, we can also apply it to differential cost analysis. Now that we have translated everything into a purely existentially quantified system of linear constraints over these template variables plus some additional variables that are introduced, we can solve the linear program to compute the PF and anti-PF and the threshold value. Moreover, we can even add the optimization objective to try to optimize the threshold value, so to compute as tight one as possible. So what are the key features of a method? First, it's fully automated. Second, as I said, it supports numerical programs with polynomial arithmetic and potentially non-determinism in the programming language. So we allow assignments of the form x equals non-det. It can be used to optimize real value threshold bounds or to verify concrete real or, let's say, polynomial bound by simply plugging it in instead of the symbolic variable t. And finally, our approach does not assume any syntactic similarity between programs. So you can pass it to syntactically very different programs and reason about their difference in cost usage. This differs from the previous works on relational cost analysis, which in a sense try to exploit syntactic similarity and align the programs. So we do not exploit syntactic similarity, but on the other hand, our approach is applicable to syntactically very different programs. We implemented the prototype of our approach with the goal of answering the question, can we compute these threshold values in practice? Tightly, of course. And to answer this question, we consider benchmarks collected from the literature of two classes. So first will be the benchmarks that are collected from the literature on single program cost analysis with patterns that have been shown to be challenging for cost analysis. So loops, nested loops, conditional branching, non-determinism. And the second benchmarks are benchmarks collected from the literature on semantic differencing, which have the same cost usage because they're semantically equivalent, but they syntactically differ. And in order to have finite threshold values so we can actually see how optimal they are, we assume that all our inputs are between 1 and 100. And the table on the right shows our results. So the second column are actually tight values, which we computed by hand. The third column is what our tool computes. And as we can see, we compute tight threshold values in 14 out of 19 examples, which shows that our approach can reason about these complex patterns and compute tight bounds. Of course, the question is what happens with the remaining 5. And here we observe the limitation that because we do not do disjunctive reasoning, we cannot get tight bounds here. So it was observed in previous literature on single program cost analysis that sometimes when you have more complicated conditional branchings, you might need operators such as max or min to capture exact cost usage. Our templates are polynomials, and Handelman's theorem is not applicable to piecewise polynomial templates. However, in the paper, we do discuss some concrete ideas on how to overcome this limitation. In particular, at least how to go to the piecewise linear setting. And this is a very, I would say, like natural next step for future work to actually get precise results even in these examples. Okay, with this I would like to conclude. So we present a new approach to differential cost analysis, which is based on simultaneously computing potential and anti-potential functions. The key features of our approach are full automation, support for polynomial numerical programs with potential non-determinism. We can optimize and compute tight real value thresholds or verify polynomial threshold values. And our approach does not require syntactic similarity, so it's applicable to syntactically quite different programs. Our experimental evaluation demonstrates the ability to compute tight threshold values in a number of challenging examples collected from the literature. And finally, as I said in the previous slide, the future direction would be, of course, to extend it with some disjunctive reasoning to get tighter bounds there. Thank you. I would be happy to take questions.
Thank you, nice talk. I was wondering whether such an approach could be generalized to other kinds of relations between costs. So in your example, it would be natural to look at the ratio between the costs rather than the difference. Is that something that one could kind of translate the approach to?
Yes. Especially as if you want to verify the ratio between two costs, then everything would still remain even when you translate it linear. If you wanted to compute a ratio between costs, then you might end up with a polynomial system of constraints. But if you wanted to verify a given value, then yes, you can absolutely, everything would remain linear. So you would still translate to some, it's just a question of whether in translation you will get linear or perhaps quadratic term due to the multiplication.
Okay, thanks.
How do you get the cost, atomic cost for each transition? Is that something predetermined by yourself? Or?
No. Yeah, we assume that we already have a cost model, so that we work with a system where like we have this already like tracking variable cost, which is used to. So for runtime, of course, this would be natural. Like let's say every operation incurs cost 1. For memory or thread allocations, you would have to essentially have a model for each operation in your program, and then from that extract the cost usage or release.
Okay. So can I just do it the other way around? I have some target gap bound, right? So and I want to boil it down to some upper bound for the atomic transition, right? So this transition has to be implemented with well, fixed budget of costs.
Such that like what is the maximal cost of an operation such that the difference in cost usage does not exceed something that
Right.
you can certainly do that. I need to think about whether the translation of Handelman's theorem will result in a linear or quadratic system.
Mhm.
But if you know exactly what you incur, I think everything will still remain linear because the cost is always linear term in this. So I think you could even do that with just linear programming, but definitely with the quadratic.
Okay, thanks.
The threshold is a constant that you need to fix, or can it be, for example, like the difference of a polynomial?
Can cost be a function of variables, essentially, polynomial?
Yeah. So, for example,
Yeah.
like so we have some cost analysis implemented in FAIR, and when we run it and we see the difference, the only interesting difference for people, for developers that we have seen, is like when, say, a function from linear becomes quadratic or becomes of a different polynomial. Then they care. Otherwise, if the difference is just constant, they don't. So yeah, I don't know how it works.
So the question: can we observe the difference in polynomial degree? Yeah. Maybe not directly using this, but you could modify the approach of perhaps if you fix in advance polynomial degrees for potential function 1 and anti-potential function 2, at least at the initial state, then you could use that to verify that there is a difference in polynomial degree actually. You would need some smart search strategy to actually decide on which polynomial degrees to check.
All right, so that's the end of this session, and thank you everybody. Thank you, speaker, and enjoy your lunch.